So next week I've added this node for what to do this. Sorry, last week I added this node for what to do next week, which is now, and that's to look at this look ahead here. So we added a bunch of code for computing the follow set of a rule or of a token, which is basically all the tokens that can follow a particular item in the grammar. And that seems to work well. The problem is we're using it wrong. So in here we should not use the follow set of this del targets rule because del targets can occur in different places than just this. And instead we should really look at what follows, what can follow this look ahead, which in this case is whatever can follow this sequence, and that is whatever can follow del statement anywhere in the grammar. And it can get more complicated. This look ahead here, so we need to look at what follows this look ahead, which is whatever follows the sequence, and that is whatever can follow this choice, which is whatever can follow the sequence, and that's whatever can follow with item anywhere in the grammar again. Does that make sense? And now that
yes, that does make sense. Sorry.
Right.
You got distracted for a little bit.
Now that I said that, I might have a better idea of an algorithm of how to get there. So let me do this. I will run the script here. I will get rid of these simplifications. Just comment them out. Which will unsimplify some of the look aheads we already got rid of, like this if in front of if statement. But we should be doing this correctly without as much code for all the possible cases, right?
Okay.
I'll put this on my screen that you can't see, just as a hint of what the different methods are called. So I think where this should go is it should go into simplification of positive look ahead, right?
Yes. Yes.
So there should be a method called simplify here, and it should be, if some condition holds, then we return whatever the name for empty sequence is. Empty, huh? So we return empty. Otherwise, we return the superclass definition. Right? Does that make sense?
Mm-hmm.
Okay. And now, what should this here be? So, so we need some kind of the follow set of this look ahead, right? And if the follow set of this look ahead, or if the tokens in this look ahead are a subset
No,
a superset.
Yeah, we stumbled upon this before as well.
Right.
No, wait, you're turning empty. Oh, right, because it's. No, we need to error in some cases, right? If if this condition does not hold, we should error. No?
Hmm. So
No, no, you shouldn't. We shouldn't. Wait. No,
if we
I'm getting
should
confused. I'm sorry.
error, that means this look ahead is not satisfiable at all, and it should not be in the
Yeah,
grammar.
no. Yeah, no, you were right before. I think it's is subset.
Right.
No.
Uh,
Is it? Oh my god, I'm so confused. Okay, so if
Superset. Subset. Ah, I think it is superset.
what is this supposed to return?
So
Is it
it's
supposed to return the
supposed
single
to return the replacement for this look ahead.
the replacement? So it
Right.
should just be
So this is
this was satisfied.
so so this means this look ahead.
I think it's gonna return empty in both cases. We have to do something. We have to do a side effect to change things.
So this look ahead must
right?
always be satisfied, which means, let me just write this out in English. This look ahead, or no other tokens than what's in the look ahead can follow it.
I have an idea when you're done writing it.
Right? Yeah, go ahead.
What if simplify didn't take just the look ahead, but no. I was gonna say the next non-terminal or next node as well, but that doesn't make sense. So you have to look at the whole rules.
So, well, we have the set of all tokens that can possibly follow this look ahead.
Yes.
And
the problem is that
if they're all
the replacement.
if they
Yeah,
all
sorry, go ahead.
appear, so if all of these appear in the look ahead, then the look ahead is useless.
Yes.
Right?
But if some of them don't appear and the look ahead actually does something, do we need to return the look ahead itself?
Then we need to keep the look ahead. Because the
Oh yeah, I see. Yeah, okay, I was getting confused there. I see the point now. Yes, you're correct.
Right. So
I assume super.simplify will not. I will do something smarter than.
So this means no. So what's in the look ahead has to contain the follow set. Yeah, so this should be right. Okay, and now we just need to get these two sets ready to go, right? So tokens in self. Well, I actually just commented out the code a minute ago. So
okay.
the look ahead. Self.item. So if whatever's inside the look ahead is a choice, then we say the tokens are the set of the items in that choice. Right? Otherwise, the tokens will be the set of the single token.
Just making sure, is it self.items dot items?
Yeah, self.item is the thing inside the look ahead.
Okay.
Right? So
otherwise it's gonna be a set with, oh, okay, yeah, the singleton set.
what do you call the thing inside the look ahead? This
let me check Wikipedia.
content.
Look at it. regextutorial.org calls it an element.
Yeah, that's basically the same as item, right?
Yeah.
So maybe self.item is the best word. So this would be the set of tokens itself, except we have to check if they're actually tokens, right? And do I call them tokens? Yeah. So if they're not all tokens, then we don't do anything.
If not all existence.
Right?
If not, so you're checking for non-terminals.
Right.
Right.
Well, no, they're terminals. Or, well, not terminals. Sequences, all of that. And actually, all of the look-aheads in the grammar are just tokens, except for one, which we should probably ignore altogether.
Okay, that makes sense. Yeah.
Okay, and now we need to compute the follow set, which that'll be the tricky part, right? So let me try to sketch the algorithm I have in mind. So wherever the look ahead appears, we can't just look at the look ahead itself, but if we need to look at whatever it appears in, right? So whatever follows this look ahead is whatever follows its position in the sequence that contains it, right? And if it appears at the end, that means we need to look at whatever follows this choice that contains that sequence, right? And that's again in a sequence, so it's whatever follows this or it's not a choice, it's an optional thing.
Sequence.
It's an optional sequence. So whatever follows this optional thingy in this sequence, and so on. So when we're doing the simplification, we're doing recursion, right? So to simplify this whole rule, we recurse into this optional thing, and then we recurse into this sequence, and then we
Mm-hmm.
do go on and on and on. But to find the following tokens, we kind of need to go backwards, right?
Yeah.
Yeah. So in the
Do we need to do we need to start storing the recursive?
yeah, we need
I
to
don't know.
start storing the path how we got
Oh boy.
how we got into the tree, right? So if we look uh, in the theory, this is simple because it just has sequences,
Mm-hmm.
right? So the position you are at in this rule is just a number, but the position you're at in our model is a tree path, basically. Does that make sense?
Yes. I'm gonna just a quick googling to to see if there are like simpler algorithms, or just to do some research on this. And you keep on doing that. I'll keep on listening, but I'm also gonna do some research in the background.
All right, that would be helpful. So
LR1.
I guess we need a path. We need some kind of tree path as an uh, argument to the simplify, and what will that tree path be? That needs to be a sequence uh, of like individual node addresses. So I guess we need to store the node and the position within that node where we are. I guess the position will mostly make sense for sequences, but we might as well add it everywhere. That makes sense?
Mm-hmm.
Uh,
I found a
so
book recommendation for 150 pounds, so that's not happening. But yeah, go on. Sorry.
it's probably somewhere in a book. Okay, so this path will then be a sequence of, let's say, pairs that contain a node and a position. So we need to take the parent, so the last thing in that path, and so the parent would be let's do a function for that. Okay. And now we need to go put this path in every call to simplify we make. So
Okay, let me take a quick look here. You go on. I'll catch up.
every def simplify will now take a path. Simplified rule set doesn't need to do that. Simplify item needs to this. Um, Adding path argument to all the simplify definitions. Still don't really know what I'm looking at, but maybe it'll become clearer as I modify the code.
Yeah, just as an update, real quick.
Go ahead.
Everything I find is related to computing the grammar, like actually recognizing a string
Right.
instead of simplifying it. So it's maybe there is some content out there, but it's not easily accessible about this. Like
Yeah.
simplifying grammar is not exactly very a very common query.
Yeah, I would imagine that. Yeah. If you're a mathematician, you basically don't really care about the efficiency of your algorithms or about, if the grammar is infinite, it's fine.
Yeah,
You can
yeah.
still say
Oh, hello.
whether a string matches or not.
Hello.
Hello, hello.
Okay. Hey, guys.
Hey,
Sorry about
Blaze.
that.
How are
Oof.
you?
I'm well. I'm well. I slept through the first alarm, and anyway.
I know how that is.
So,
Yeah, we have some catching up to do with you.
yeah, we
A lot of
do.
things.
So,
Uh,
uh, we've been looking at some theory.
Oh, really?
Yeah, it's interesting where this gets you. So, uh, there's a look ahead here and with statement,
Okay.
right? So the with statement uh, is defined as async with, and then you have a comma separated with items, either on its own or in parentheses.
Yes.
And then you have a block after that, right? But the with item, that one's interesting. That's an
Mm-hmm.
expression, and then after that expression, there's optional as some kind of target, and then there's this look ahead. And this look ahead is here, I think, only for efficiency. If it wasn't there, Python would behave the same way, right? So we don't need that in the documentation. And we
Okay.
can see that quite easily because the with item only appears here, right? And after this with item, we can either have a comma or this comma or closing parentheses.
Right.
After this with item, we can either have this comma or this colon, right? Nothing else can come after a with item,
Mm.
right? And this
Yeah.
lists these three tokens that we just found,
Right.
right? So we need to find an algorithm
Oh, Jesus.
to do this, right? So
Yeah.
there's the positive look ahead class that we have. It's an instance of look ahead, which basically shares it basically shares a lot of stuff with negative look ahead. Before we started looking into what it actually does, it just has
Mm.
different symbol in the string representation. Otherwise, it's the same as before. But now to simplify, there are two parts here. The first one is find all the tokens the look ahead contains, right?
Yeah. Yeah.
We don't simplify look aheads that contain more than tokens, right? So
Right. Yeah.
there are two things we look for. One is a choice that contains tokens, and one is just a token, so we get a set of those, and we check if all of them are tokens, and that's the easy part. That's that we have tokens in this look ahead, right? Now this is the hard part, which is all the tokens that can follow this positive look ahead based on the grammar, right?
Yeah.
And now, if no other tokens than what this look ahead contains can follow the look ahead, then the look ahead is redundant, and we can replace it with nothing.
Oh, okay.
Right, and this is a real head scratcher, right? We're pretty sure it's right. It'll need some testing. But you know, this is not the hard part. The hard part is this the set of tokens that can follow this look ahead, right? And how do we compute that? So we have this look ahead. What can follow it? Well, that we can find out as whatever can follow the sequence that it's at the end of, right? That makes sense?
Oh, yeah, sure.
And
yeah.
what can follow the sequence that's inside this optional element? Well, whatever can follow the optional element can also follow the sequence, right?
Yeah.
That optional thing is itself in another sequence, so whatever, well, it's at the end of the sequence, so whatever can follow this sequence can follow whatever, that's the follow set we're looking for. So in the end, we're looking for whatever can follow with item in the entire grammar. Right, and since with item appears there and there, then we repeat the this kind of search for this occurrence and this occurrence, and we combine all those sets together.
Okay.
Does that make sense?
Yeah.
All right. So how do we do this? So when we're doing the simplification, we're kind of walking the tree recursively.
Yeah.
But here we kind of have to walk backwards, right, to the thing that contains it, contains the thing we're simplifying, right?
Okay.
So when we looked at the theory, that was kind of simple because this only has sequences of symbols here. So the position in the sequence is just a number. But here we have a tree, and the position in a tree is a path.
Yes.
Right? So as we're doing the simplification, we need to keep the track of the path of how we got there, and then we can backtrack using that path. Does that make sense?
Mm-hmm. Yeah.
Yeah, so well, now all that's left is to put that in code somehow. Right?
Should we like read it in? Do we read it into and then start at the end? Like work our way back?
Well, so here I'm calling a function called follow get follow set. So the follow set is the technical term for the set of tokens that can follow something in the grammar, right?
Right. Oh,
so
okay.
That's like the
oh, I see.
term
Yeah.
from the theory. But that will I guess path is fine here, right? So that'll be a function that'll basically depend on the tree path, and it'll also need these rules, right? And before I even get to defining that function, I need to get this path as an argument to all the simplify methods in the code.
Yeah.
Right? Okay. So I've added path arguments to all the definitions. Now I need to add it to all the recursive calls, and I'll just use test-driven development like approach of looking at the error. So the error is at 816.
Okay. Super cool.
So convert grammar. This calls simplify node. And I think this is the first call, so this needs some kind of root path, and I think the root path. So there are. I don't know how familiar you're with the code currently, but there are two simplification functions. There's a simplify node function which calls the simplify method repeatedly, right?
Oh, I think I remember this part. Yeah.
So instead of like doing some optimizations to make sure that it's simplified in one go, we just simplify each node over and over again until it stops changing, and then it's simplified, right? So the way you're supposed to or the way the code is supposed to work is the recursion in the simplify method should call simplify node, and the simplify node then calls simplify on the given node, right?
Yeah.
So I think the correct place to grow this path is in simplify node, right? So this should get some kind of path to the parent, and it appends this. Or should it?
This
Oh,
stopped
maybe
it.
not.
Yeah.
Maybe not. Oh, maybe not, because the path entry depends on where we are in the node, right? So if we're in the sequence, we not only need to know that we're inside the sequence, but we also need to know that we're at position 2, right? Right. Okay. So we can't add to the path here. We'll need to add in each recursive call to simplify. Okay. I wonder when this will be complicated enough that I'll stop understanding it. So the path, let me name things as much as possible. So the path should be a sequence. I guess it's best to use immutable sequences. So this will be this isn't convert grammar. So the path to this node will have one element. And that'll be a path entry for a rule, which is kind of special. Or maybe we can think of it as a path entry for the grammar itself, right? Let's make none stand for the grammar itself. Where are we in the grammar? That should be identified with this name.
Oh, wow. Okay.
Right? And then we'll add more path entries after this one. Does that make sense?
Yes. This is, yes. Amazing. Okay.
All right, now path entry will be a data class. However, I've
Yeah.
Imported data classes. Let's make it frozen.
Yep. Frozen. Yep.
Just to make it immutable, and it will have the parent node, and it will have the position, which depends on the type here depends on the node, so this will be just anything. Right? If this was a type-safe language and not Python, we'd have, I don't know, a sequence path entry where the position would be an int, and whatever, decorator path entry where you'd have no position and so on. I guess I'm cheating here because we also have none.
Right. No parents.
Right. So we could either have a none here, or we could just leave the path entry out, but we don't want to leave it out because we need the position in the entire grammar, which is in this case the name. Right?
Yeah. Yeah.
And now whenever we call whenever we recurse, so whenever we call simplify node for a new node, we'll need to append a new path entry to that path. I wonder if this needs to be a sequence, or we'll just make it a linked list.
I'll be right back. Keep
Yeah, because if it's immutable, we can't append to it, though, right?
No, we can make a new one that references
new one.
to
I see.
like this one.
Okay.
Right, parent entry can be either a path entry or none.
Okay.
This would be the node and the position within that node.
Okay.
Right, so the root will be this. Oh, and this. I hate typing. Typing.union. So this is a shortcut for typing.union, but I can't use the class name yet because the class is not defined, so I have to use it as a string, but string doesn't have this operator. Typing in Python is an afterthought, right? And I need to import typing for that. Even though I'm not really using typing here, but data class is needed. Alright. And we can define an extended method which returns a new path entry with this parent and the node and the position. Does that make sense?
Yeah. Good.
Right. Okay. Now let's look at the error here, and let's look at 267 here. We're calling simplify item, and somehow I have added the path to simplify item. So the path for simplify item will be the original path dot extended with self and the position within self which I don't know yet. Here's the index. That makes sense?
Yeah, so far.
So it's not a sequence, so maybe not an extended. What should this be called? A child? I don't know.
Sure.
Yeah.
Or a node.
Naming is hard.
Naming is hard. Yeah.
Alright, now we're simplifying a sequence and we're going again through items in self, so we need to do the same trick. Like this. Now we go to line 550 and this is an optional decorator. So this is just a super call. So that should be fine. Whoops. But we do need to add the path to the decorator simplify. Like this simplify node, right? So this is recursing to simplify node, so this will need to call path.child self, and since decorator only has one thing inside it, it doesn't need a position. And we set a default position to none. The next thing here is we're calling simplify node inside wherever we simplify choice. So this will be the child here. And this is a bit tricky. Because we are creating a new sequence which doesn't have a parent yet.
Right.
Right, so we can only simplify this. We can now only simplify things if we have the whole tree of things that are defined in. It's a bit unfortunate. So I wonder if we just don't simplify here. should work because simplify node is gonna be called eventually. Might take longer. Hopefully it'll not take infinitely longer.
I wonder if we could. Is there a pattern we could match on, like a match case?
Like what?
I'm thinking of match case, like where I wonder if there's a pattern that we can look for before we do anything. In other words, because it seems like we have to do a lot of stuff
Maybe
every
like
single time.
where there was some code we commented out that was basically a match case, but it didn't encompass all possibilities. It only worked for the grammar because it has some bias in the code. Like there's some, what's the term? Not
Yeah,
hidden
this is what.
rules.
Yeah, this.
Yeah, this.
That
This is what I came up with before, but it only like targets specific cases. Like this case was
Okay.
pretty successful in eliminating
Okay.
some of the look-aheads, like
Right.
the ones that aren't at the very end of a rule, but I think the ones that were just at the start of one.
Okay.
This would have eliminated cases where we have non-terminal, so reference to another rule followed by a look-ahead, which is all the remaining cases, but it didn't actually work.
Okay. Well, I'm encouraged that my intuition led me to the same mistakes that you made.
Yeah, that's always good.
That's awesome.
So that's what we ruled out a week ago. And I'm stuck here, updating code, path. So, oh, is that it? It's interesting. So by the time the tool gets to the first positive look ahead, I guess all the simplify node calls are now handled.
Yeah, that's super cool.
Well, I mean, not all of them. There's still like simplify node here for some reason, but that's fine. Okay, so now I will need to define this get follow set for path. So what does that mean? That'll need to look at this path. Let's do my favorite match statement here. So if the path is a path entry where I don't care about the parent, the node is this is a node, and I don't care about the position, so I probably don't really need the path. I just need to look for the node. So if this path corresponds to the node, I should just follow the just ask the node.
Kitty alert. Let's see if she says something. Kitty. No? You don't want to talk? Okay, fine.
don't know if I'll need this function or not.
Cool.
So this path to the positive look ahead includes the entry for the positive look ahead itself. No, it doesn't. It just has the parent of the positive look ahead. So here in that function I just defined, I should be asking the parent, which is the sequence here, about the follow set for a particular path. And now we can go to the sequence class and we already have this get possible start tokens for a sequence that we defined later.
You'll probably have to create some sort of index for each node when in sequence, right? So you can fetch the next one or recursively go up a level again.
So,
or am I crazy?
Okay, so let's look again how this get possible start tokens works for sequences, right? So what do we do here?
Actually, sorry about this, but I'm actually gonna have to go now.
Oh, okay.
Right.
Yeah, it's about time. Sorry about this. Do you let me catch me back up next week? I'll be
Yeah.
back.
Yeah, definitely.
Okay,
Okay.
cool.
Have a good one. Good luck.
Bye-bye.
See you next
Bye.
week. I think it's always good to summarize and repeat what we did
Yeah.
here. Because, well, I hope this is the most complicated thing that will be on the stream.
Yeah, me too.
But hopefully we can simplify this. Alright, so you weren't here when we wrote this function get possible start tokens, right?
No.
Okay.
No, I don't think so.
So this is a method that most of the nodes now have, which gives us all of the tokens the sequence or whatever node can possibly start with, right? Does that make sense?
Yeah.
Right.
Yeah.
So I don't know, this with item or can start with whatever this expression can start with. So if I go in there, expression can start with conditional expression, or it can be a lambda expression. So we look at whatever this can start with, whatever that can start with, combine those two sets, and we have the set of tokens, right? Look at conditional expression that starts with an OR test, which somehow oh, that was the old grammar. In the actual grammar, expression starts with disjunction and nothing else. Oh, or lambda def. So again, we have to take the union of those two sets. Disjunction, goes to conjunction, inversion, comparison, bitwise or.
Wow.
Yeah, this is the expression grammar. It's kind of crazy. It's really nested.
Amazing. Wow.
So here's an interesting one. So this can start with a weight or whatever primary starts with, and so on and so on and so on. So primary can actually start with primary, so we get infinite recursion here. But the way to solve it is just ignore this primary because it cannot add any new tokens the primary can start with, and we just look at the other stuff. So this can be either bracket or name or true or false or blah, blah. So this is very close to the set of tokens that Atom can start with, right?
Right. Right.
And
wow.
so that makes it very close to the set of things that expression can start with.
Yes.
So, uh, so that's the gist, right? We have a method that takes this sequence and gives you the set of tokens that could ever be at the beginning of it.
At the beginning, yeah.
There's one quirk that makes this hard, and that is expression, or, well, maybe not expression, but anything in that sequence, like this optional thing, can match the empty string, right? So if expression here could be empty, then with item could also start with whatever's here.
Okay.
Right?
Oh my god. Oh.
Yeah, so that's a bit of a complication.
Wow.
So the way we solve that is get possible start tokens can returns a set, but the set can have either tokens or none in it. And none means there. I mean, this could be empty, right? Does that make sense?
Yeah.
All right.
Wow.
So what does this do? If there are no items in the sequence, we know where we're at, so we return none. Now this sequence can only be empty, and it cannot start with any tokens, so it can just be empty. And then there's a loop that usually terminates early. So we go through all of the items. We get the possible start tokens for each individual item. We add all of them to a result set. And if we find that none is in that result, is in those start tokens, so that means this item could expand to nothing at all, then we need to continue, right? So if the item can be empty, then we continue the loop. Otherwise, we remove any none from the result, because now this sequence itself cannot be empty. We found an item that needs to have a token in it, so we discard that none, and we break, and then we return the result. Does that make sense?
Yeah.
Right.
Yeah.
Why is this important? Because now we need to define this method get follow set for path, which for a sequence basically means what can follow a particular position in that sequence, right? So if we're in this sequence and we have the path here, then we need to look what can follow this this item that we're looking at, and that's basically the same thing as the start tokens for the entire sequence, but we don't start this loop at the start of the sequence, but at the position we're at. Does that make sense?
Yeah. Wow. All right.
So to make this easy right now, I'll just copy it and I'll set the items are a subsequence of self items starting at position and continuing to the very end. And then instead of self items, I just use items, and it should be basically the same, but I need to get rid of the special case and start with none. So basically start assuming that
that it's empty.
We can go on, that it's empty, so that if there are no items at all, we just return the result. And otherwise, whenever we break, we'll not have none. And if the for runs its course, that means all of the items can be empty, so the none returns remains in there, right? So I basically got rid of an optimization here, right? And now the problem is, if this for loop does run its course, then the follow set for this sequence needs to include whatever whatever can follow the sequence itself. Does that make sense?
Yeah.
Right. So if the none is in the result, then we discard it. We don't really want it, but we also update the result with whatever that function was called, get follow set for path. Like this. Right, so we get the follow set for the sequence itself. Does that make sense?
Yeah.
I hope it does.
Right.
And
Yeah,
this,
so far, yeah.
and this position is path.position, right? And we assert, same thing, that this path is actually for this node, right?
Right. Oh, yeah. Okay. Would it ever not be? I guess.
Well,
We're just
if we made a mistake and this path actually
Yes.
meant something different than what I assume in this
sure.
function, right? Because
yeah,
I'm just writing this, assuming that path is in the most convenient form for this function, but that might not be the most convenient form for the caller. So rather than go and check, I'd rather assert this and let Python tell me.
Yeah.
All right. Now we get a type error here. So if we have a choice, the items in that choice can be a list. Whoa, what? There's something about this code base I don't know. What is that? Oh. The items in a choice are lists? Oh no, the sequence can contain a list. Yeah, I think I need to do this check before I convert to set. And that's okay. Just keep it as a sequence here and then convert it to set later. Yeah, that makes sense.
Oh, that's slick.
Yeah, I need them all to be tokens, but if they're not tokens, then I cannot. Then I might not be able to use them as select elements. So we need to do that after the check. Well, that's a diversion. Super simplify rules and path. Right, now here we are simplifying a sequence, and we're recursing into simplify item. And I don't think we can really simplify items directly here because those items will those items will now have some kind of wonky parents, so let's not simplify early here and rely on the simplification loop to reach a fixed point. Right, so now path entry doesn't have an attribute called parent on line 519 here, because the attribute is actually called parent entry. Now the choice object doesn't have get follow set for path.
Get follow set for path. Okay.
Yeah, that's this thing we we just defined for sequences. And I see one error here. We're looking at items starting with the position we're looking at, right? So getting the follow set for this item within this sequence would start with that item itself, while it should start right after it. So I just see an off by one error that might not be easy to debug later. Right, so now I have to define this same method for choices. You remember what this method does? Gives me what can follow a particular item in
that's right.
in a sequence. Yes. Right? So all the tokens that can follow something in a sequence. Right. Now I have a choice. So the same thing for choice. So I have a choice of several things, right? And I have, let's say, thing number 3 here, and I'm looking at what can follow thing number 3, which is hopefully much easier than the sequence choice, because whatever can follow item number 3 is exactly whatever can follow the choice itself. Right? So we use the get follow set for path's parent entry. Right?
Yeah.
Okay, that should work. And that needs the path, and it also needs reference to all the rules. And with that, it looks like we have recursed to the top of the tree.
Sweet. Okay.
Right, so I don't know where exactly we are. If I look at the traceback, so if there's some kind of setup, then we call node simplify items, simplify node, simplify, so we're recursing down and down and down and down. And
that's so cool. Okay.
Now in here, we start recursing up. So we've built up this path using the path.child. I guess we're only 2 levels down. But we start recursing up, and we use the parent entry. So 2 childs, 2 parent entries, and now we're at the start of whatever rule we're simplifying here,
parsing.
right?
Yeah, simplifying. Yeah.
So we're right back at the top level and getting this not implemented error. because path.node is none, which means we're at the entire grammar, right? And here, so what does this mean? This means we're looking at for the follow set of an entire rule like this with item, right? So basically we're here at the end. So we've recursed up from this sequence, from this optional, from this top level sequence, and we need to know what follows this sequence. What tokens can follow this sequence possibly, right? And for that, we need to get this name, look at all the places where this rule appears in the entire grammar, and see what can follow these occurrences. Does that make sense?
Yeah.
Right. And
Sweet. Well, how?
how? Oh, we need to
This is
search the
great.
grammar for with item
Okay.
and see what can follow it. And I think I've written some code for that before.
The follow set.
Yeah, that's get follow set. And all the nodes have get follow set. It should probably be done as methods of the nodes, but yeah. So non-terminals have get follow set, and that's the only thing that has get follow set. So this self, I mean, only the value for of self is used in this entire method. So instead of self.value, since it's a non-terminal, so that's a reference to the rule, right? Like this thing is a non-terminal. I can just use the rule name, right?
Oh.
So let's not make this a method. Let's make this a function. And it'll be called get rule follow set, and instead of self I'll use the rule name. Nice name. Yeah, there. Let's be specific. And instead of this self.value, I use rule name. Hopefully that's it. And yeah, so I return get rule follow set with now since path.node is none, I'm using the root path entry where position is the name. So the rule name is path.position. I know the rules, and yeah, this thing also needs this rules are considered need to adjust the recursion here. So now we have a problem somewhere. Ah, dear. So yeah, this is a weird thing in Python grammar where if I replace self.value with this rule name, it changes the meaning of the entire case statement. Because before it had a dot in it and now it doesn't. So before it actually checked if the non-terminal's value matches this expression. But if I just have a simple name in there that doesn't have a dot in it, it assigns to this variable. And that's very tricky, and I'm not not really used to editing the things in these parentheses. Need to be kind of careful there. And the recursion here needs to use get from follow set. Right, so let's go on. And here I have simplify node, and I'm calling it from a function called simplified rule set. So I guess this should use some kind of root path. Maybe. So this is a root path, right? This is a path for a top level, like a grammar rule named name. Are you following?
Yeah.
Right, so maybe I'll name that. I'll make a class method. Right. And this should make an instance of class path entry with none, and the name of the rule. And now I can replace this with path entry dot root path with the name, which is a bit more explicit, I hope.
Mm-hmm.
And I'll do the same thing at line 944 when I need a root path for this rule name here. Right. So far so good. So no real debugging so far. Just adding the necessary methods. So one or more object has no attribute get follow set for path. So I get to the definition of one or more, and one or more is kind of like the choice, right? So if I want to get follow set for the thing inside of one or one or more itself, I just ask its parent, right? It's not really a sequence. There's only one position in the one or more
A list.
that we can have, right? So
Yeah.
so the get follow set for path, what's the definition supposed to look like this self path rules. So I basically ask the parent.
Yeah. Oh, right. You just took.
So that's and parent entry. Like that. also need to include the possible start tokens for the thing inside this one or more, because that thing can be followed by itself. Does that make sense?
It can be followed by itself? Start token. Start tokens. Okay.
Right.
Cool.
Yeah, so I'm looking at what can follow the contents of this repetition.
I see.
Right. So
Right,
wherever I am in the repetition, then it can be followed by whatever that item can start with. Right.
Okay.
If that item can be empty, I don't really care. So I just call that
nice.
that.
Sure.
But then that thing can be followed by whatever the next item can start with, or the item after that. They're the same thing. Plus whatever this one or more itself can be can start with, and it's a set, so there's the operator's a pipe rather than a plus, but otherwise this should be fine. So that should be it, and this is not item, this is item. Did I make a typo here? Alright, now the same thing for 0 or more. And for 0 or more, we're pretty much in the same situation, right?
0. Yeah.
Right, now there's gather. So gather is a sequence of items. There has to be at least one of the items separated by separator, right? So what can follow so we need to look at the thing that that we're asked to compute the follow set for. It can either be the separator, and let's not use 1 and 0, let's use string constant, right? So so the position in the path can be either the separator, or it can be the item and nothing else.
Oh, cool. Okay. Yeah.
Okay. Now, if this is the separator, I think we'll need start tokens for both the separator and the item. Alright, so if this is the separator, we need to look at the item start tokens. because the item can definitely. I mean, the item can definitely has to follow a separator, right?
Yeah.
Okay. But if the item can be empty, so that means if none is in the result, then the separator can be followed by itself. Right?
Yeah, yeah.
And there could also be no separator at all. So we need to look at what can follow the gather itself, right?
No. Oh, we mean like if it's at the end of a.
Yeah.
Okay.
If the so we're at a separator, so an item needs to follow, but if the item is empty, then we can have either another separator and item, or the entire gather can end, and we need to look at what comes after it.
Okay.
We can discard the nones now and return result. I guess. Right. And now if we're at an item, then we definitely the item can definitely be followed by a separator. Right. And it can also be followed by whatever the gather can be followed with. Right? And if the separator can be empty, then it can also be followed by another item. And I don't like how complex this logic is.
It's.
I think we might need to write some unit tests after all.
Yeah.
Oh, wait. Oh, was that it? Did it run now?
It hasn't failed yet. Oh my gosh.
That is. So it didn't raise an error. And it's removed.
Yeah, it's doing stuff. It's removing. Oh my god.
It's
Ta-da!
wow. Yeah, but it's removing the wrong stuff.
Oh, it is.
These are exactly the things that it should not be removing.
Oh.
I mean, this import or from, that's fine. That's great, actually. An import statement can probably only start with import or from. Strings Oh no, it left in. Sorry, the green stuff is yeah, it left in uh, stuff that it should uh, remove, and it removed stuff that should have been left in. So it looks like the logic is all skewed, but I'm worried by this. So start expressions doesn't really have any look ahead in it. And that got de-optimized rather heavily. I think there's a bit of a problem here. It's probably where we removed those optimization calls and relied on the repeated optimization to kick in. Apparently it didn't, because what happened here is before this was optimized into a gather, and
Yeah.
now we don't have the gather. Does that make sense?
Yeah. Okay.
Yeah. Alright. Yeah, all of this stuff came back, which is not great. This came back, which is not great. Right, so now the problem here is I wrote a lot of code, and there's probably some kind of mistake in it. And it might be time to start writing unit tests for this.
Okay. I'm a big fan of learning to write unit tests.
Yeah. Might be good for next week though.
Yeah, of course.
So the problem here is so far we've been testing just with the grammar we have, which is kind of complicated. So now we need to debug the grammar we have, and that doesn't really look easy. But we only have 15 minutes left, so what I would like to spend those 15 minutes on is putting back the simplify called we had this in sequence somewhere. Right, this one. We called simplify node on a sequence alternatives. So that was, or maybe not in sequence, maybe in choice. So this one. So before the change, it was this. Right, so I just changed this into that, which I think broke stuff. So let's bring it back, and we simplified the node here. Now simplify node needs some rules, some node, and now it also needs a path. Let's give this some breathing space. So like this, it'll be missing a positional argument path. So what do? I give it a path. So this needs to be a sort of fake path.
Oh.
Because I've just created this sequence. The sequence is not actually a child of this this choice. Right?
Okay.
But I'll still say treat the sequence as if it was part of this choice, and the position in the choice, I mean, that doesn't really matter for what we're using the path for right now. So let's lie. Let's put in none. It doesn't have a position.
Sure. Ooh.
Ooh, wow.
It seems happy with that.
I mean, it fixed the del statement. That's great.
Yeah.
It fixed the with item. That's perfect.
Wow. That's amazing.
And about these arguments? So before it said arguments need to be followed by a closing parenthesis. Where do arguments actually appear in the grammar? Let's look at that. That's language reference, grammar specification. So arguments are here, they're optional and need to be followed by a parenthesis. Here also. Yeah, this is the definition of arguments. Here they're followed by parentheses. I think the algorithm is actually correct. Wow. Yeah,
wow.
this is not needed. Sorry. So now we have this lambda keywords. Let's look at where lambda keywords are in the grammar. So lambda keywords appear in lambda star etc, which only appears at the end of lambda parameters, which only appears at the end of lambda params, which is only ever, I mean, if it appears at all, it's only ever followed by a colon. So this look ahead is not necessary, and the simplification is correct.
Oh my god, that is so cool.
Wow, that is. I mean, I didn't really think it would actually work without debugging, but that doesn't mean I'm really confident about the code. And
yeah,
some
no, I mean, we
tests,
still need the
some
unit tests.
are
Yeah.
probably in order. But this is a great result. I mean, the code definitely needs a lot of cleanup. So what I'm not really all that happy about is this handle node function, which basically does a match on classes, which means it would probably work better as a method. So this this function is a bit complicated and specific to the operation here, so maybe it's fine, but that's something I should probably explain next week. Also, this bit of complexity can now go. And yeah, there's a lot of cleanup to do on this code, but let's do that next week if you're fine with that.
Yeah, of course.
the interesting part about this diff is that it's not really the whole diff of what this change did, because it also included the other case we did before. Yeah, this one. So the code we just added also got rid of function definition can only start with def or decorator or async. So this look ahead is also redundant. So we basically had a special case for that written a week or two ago, which already worked, but I've just removed it. That was this part that was commented out. Right, so the special case is now included in the more general case of looking what can come after this look ahead in this sequence, right? Which
Right,
is basically
right,
whatever
right.
function def can start with. Yeah, so the function definitions, the with statement can start with with or async, the try statement can start with try. All of these look aheads are here to help the parser, because when it sees a compound statement, it can just look at the first token and go directly to the relevant choice.
The next.
Right? So if it starts an if, it doesn't need to parse function definitions just to see that it won't match, right? And same here. So tuple group or generator expression can start with an opening parentheses. So we get rid of that look ahead and this sub choice following that. So now atoms are just a nice little list of choices that you can have there.
That's cool. Yeah.
And simple statements, that's basically the same thing. That was where the import from came from. So yeah, I hope what's next is breaking the lines to make this more readable, simplifying the code, maybe adding some tests to make me more confident that this is actually working. Need some adversary writing test grammars where that wouldn't be simplified correctly.
Yeah.
And then generating the diagrams, of course. But there's a lot more to-dos here. So
yeah.
Here's the to-do for with item. Remove this, which we just did.
Yeah.
That's great. Star expression, I don't know about that. Maybe we should look at the generated grammar for star expression. Yeah, try statement is apparently shouldn't be simplified at all.
Did we put test? Should we write tests to make sure these things don't happen?
Which one?
Later on? I mean, the try statement, for example?
Let's look at how the try statement works. That would be compound one. Try statement. Right, so it's this. So it's try colon, and then then there's a block, and there can be either finally block or an expect start follow by optional else and then a finally.
Right.
And if you look at it in the grammar, this is much clearer.
Yeah, it is.
Right? So what I would probably do, and that's definitely for next week, is go in the input to the tool. Wherever this is defined, and exclamation mark here to say skip the simplification for this one, please. And just do whatever, but do it exactly as it is in the grammar. This is fine. But yeah, that's for next week. Mark an alternative as optimization only. That might be for later. Oh, I'm looking at the to-dos that need grammar changes, which should probably rule out for now. Better line wrapping, simplifying the if statement, and then we have an optional sequence for diagrams only. I think we're in a pretty good shape, and the next step should probably be line breaking, code cleanup, or diagram generation. So think about what you want to hear next, and I'll see you next week.
Okay. Right on. Thank you so much. Take care. Cheers.